Alright. Am I streaming? Yes. Okay. So yeah, I haven't done this in a long time, so let me just check that the audio is decent and that I'm not speaking into the void. Yeah, I haven't done this in a long time. Yeah, okay. And so yeah, today I've ordered. Fuck, I'm retarded. I'm watching the replay. I ordered like this small microcontroller called ESP32. Apparently a pretty popular one, and so yeah, just I started to very quickly do the Hello World on it yesterday evening, and I thought it would be cool to just yeah, to just do some more random shit on it on stream, I guess. And so maybe I should put that in the description. I'm following this book because I'm writing the software that goes on the microcontroller in Rust because I discovered you can do that, so I did, and it's pretty good. So yeah. Let me just maybe put that in the description. Can I edit this on the fly? First, ESP32 book. I guess that works. So yeah, and so yeah, I just ran through the four first chapters, and now I just have a little hello world, which I don't understand what it does, but it's there. So yeah, maybe that's the first step. But yeah, I should maybe show that it runs. So this thing just prints hello world and blinks the light. Okay, no, there is no explicit like blinking the light, but every time it executes an instruction, I think it blinks the light. And so here it just says hello world every second, and so I just do cargo run release, and it just flashes the program on the chip. And well, I don't know if you can see, but it's the light is blinking every second, but I'm guessing that's quite hard to discern. And it says hello world, no surprise. So it does. And of course, yeah, there is a way to get the Rust standard library on this chip, but it seemed a bit harder to set up, so I said I wanted to do this quickly, so we have no standard library, which might be a bit annoying in the future, but oh well, for a few small tests it doesn't matter. No main, sure. I guess it just has another entry point. Oh, I've never seen this, where it returns an exclamation point. First, return this. What does that mean? First, return type is an exclamation point. What is a user exclamation point as a return type in Rust? Okay, so that's what I have. Unit is not nothing, it's a type with one possible value also, okay. Furthermore, when a function returns unit or nothing as you say, it actually returns the never type. Specify that the function never returns. Ah, okay, that makes sense. So here our main function is a function that never returns. That makes sense, it's an infinite loop. So, is there like documentations on this thing by any chance? Cargo, I don't know, Toml? So what kind of libraries have I installed? I have ESP backtrace, ESP all, ESP println. So either one of those two. Let's see. I think it's here actually. Is this it? No, it's not in Rust. They have like the Rust libraries here. So whole is hardware abstraction layer. Okay, that makes sense. That makes sense. Is there like the Rust equivalent of this here? No. Rust ESP32 whole. Okay, so for example, the peripherals, delay, clock control thing, all of those things come from ESP whole. So I'm just a bit curious as to what it does. Public archive. There's new multi-chip hole. Okay. Where is the documentation? Where is the documentation? There. I'm guessing I have just the plain ESP32. Don't know what those are, to be honest. Bare metal, no STD, whole is for all ESP32 devices. The whole implements HAL. Maybe I should call it that instead of whole, but whole is easier to say. Implements both blocking and async. APIs for many peripherals where applicable. Driver implements the embedded whole and embedded all async traits. Choosing a device, example, features. And so, for example, I have peripherals. This module creates singleton instance for each of the various peripherals and re-exports them to allow user to access and use them in their application. So that's, I guess, some kind of chips or like some abstraction over. So yeah, it is abstraction over hardware, but I guess it just supports these kinds of hardware which are standard. So Wi-Fi is standard, UART is standard, and there is a shit ton of things that I've never seen. I2C, I know. Okay, so it's like more like digital standards, I guess, that are abstracted in software. And so what do we do? What do I have? Peripherals. Peripherals. So how about structs? No. Get core. Can I just search peripherals? That's strange. I don't see the struct that they use, but borrow. Oh wait, I'm a bit lost. Delay, that makes sense. Clock control. Clock control max, system, clock control freeze. Does that control the clock rate? Is this CPU control? Is there like a clock? There is a clock. This clock driver provides an interface for configuring and managing various clocks present on the ESP microcontrollers. Proper clock configuration is essential for the correct functioning of the microcontroller and its peripherals. The clock driver supports configuring multiple clocks, including CPU, APB, Extal, PLL. Well, I know at least one of those. And so yeah, it's to set the clock speed. Okay. Once the clock configuration is applied using the freeze, okay, so freeze is like committing the clock, so here we just set the max speed of it, and then freeze makes it so that, yeah, that's just how it is. And okay, initialize with default clock frequency for this chip. Oh, okay, that makes sense. So, but here it says initialize with the highest possible frequency for this chip. Okay, I get it. So, okay. Custom. All right. And I guess we just have to do that every single time, or maybe it takes the default by default. Peripherals. Yeah, I'm guessing it's just a struct to interact with peripherals. I'm not sure. Peripheral system split. And where do you use the system? There. System. Peripherals system, okay. Steel. There's a split somewhere. Damn, that's a lot of stuff. No, it's like a split. This split the system D port peripherals into its parts. All right, whatever. I think I get it. Let's just watch some other examples. So okay, so there is plenty of. So I just did the hello world. There is also HTTP client. Is there an HTTP? Huh. So there is a ton of Wi-Fi stuff because this microcontroller has, I think, Wi-Fi and Bluetooth built in. SSID password. Okay, do I really want to leak my Wi-Fi password to the internet? I'm not sure. Yeah, I don't know. Maybe I could set it up off stream for next time. So let's not do that today. Panic. I'm just exploring a bit. Button. And so understanding the ESP template, tooling, visual serial code. Dev containers, using containers. Where was I? Understanding the ESP template. Oh, actually I didn't have to do that myself. It's just all explained here. Okay, never mind. Now that we generated the project, let's do some stuff inspecting the generated project. So yeah, generated just a thing with the main.rs. Yeah, do I really care about that? Let's just look at the code, I guess. That's pretty self-explanatory. The no main attribute says that this program won't use the standard main interface, which is usually used when a full operating system is available. Okay, yeah, that makes sense. That I just discovered what it was earlier. Use ESP backtrace. Since we are in bare metal environment, we need a panic handler that runs if a panic occurs in code. Okay, backtrace. Okay, that makes more sense. There are a few different crates you can use. For example, panic halt, but ESP backtrace provides an implementation that prints the address of a backtrace together with ESP flash. Okay, sure. Okay, that's nice. We need to bring sometimes peripherals. All drivers, HAL drivers, usually take ownership of peripherals accessed via the PAC. The hell is a PAC? pied ici. Pied ici. Yeah, I'm not sure what that is. Let mute system peripherals split. Sometimes the peripheral, here the system peripheral is coarse grain and doesn't exactly fit the whole driver, HAL driver. So we split the system peripheral into smaller pieces which get passed to the drivers. Okay, clock, yeah, that's, I think that I understand. Yeah. Running the code, since suppose the monitor argument to ASP flash so that we can see what code is printed. Make sure that you have ESP flash installed. Yeah, okay. Oh, I could have the cargo installed it. Okay, sure. You should see something similar to this. Yes. Alright. But I know that the IDF stuff is when you have the standard library installed, which is not my case. And so yeah, that's where I was. No STD application. Isn't that what I'm... Okay. Okay, it's just another book. If you want to learn more about how to develop no STD applications, see the following training materials. Okay. Repository, the training contains, okay, what I did. And so here the rest of the thing explains the tooling, which I don't really need. Troubleshooting and whatever. Okay, so let's just go on this other book, which, well, does whatever what I want. So learning the SPRIF whatever way of doing things. Introduction. Content of this material. The goal of this book is to provide a getting started guide using the Rust programming language with SPRIF SOCs and modules using NoSTD bare metal approach. To better understand this approach, see Developing on bare metal NoSTD chapters of the Rust on ESP book. The introductory trail will introduce you to the basic... okay. I don't know what it is with Rust book, but they always like to just ramble on and on and on. Looks like a fucking teenager trying to fill in the word quotas for his assignment, which is rather annoying. I mean, I guess, okay, never mind. Maybe I spoke a bit too fast because it's very light. But the official Rust book, nightmare. Good, but nightmare. Too much fluff. Examples shown here usually apply to C3 using you can use SOC supported. Okay, sure. Alright. Preparation. Recon and formatting we use. Code annotations. Required hardware. What's this? Open hardware with okay, yeah, I don't get it. I don't care. Simulating projects, don't need that. Hardware. Checking the hardware. Connect the SPRIF Rust board to your computer. Verify a tiny red controller light appear. Yeah, I mean, I have stuff appearing. Yeah, it's connected, workshop repository, I don't care. Hello world, okay. So that's already something I did. I mean, they have like extra steps, which I should learn about in the future, but whatever. Intro to workshop. This workshop guides you through the basics of embedded development. At the end of the workshop, we will be able to interact with the outside world. The content includes a panic example. Why do they want to panic so bad? a blinky example, a button example, a button with interrupt example. Alright. Panic. When something goes terribly wrong in Rust, there might occur a panic. Go to intro panic, sure. Just show me the code. Oh, I'm supposed to have cloned their thing. Generally, you want to release always profile release debug is equal to true. And so, what is their close their thing? Panic. Okay. And so they just have an infinite loop with nothing in it, and that causes it to panic somehow. So no need for this, no need for this. So this makes it panic. I mean, yeah, okay. Nothing is blinking, which makes sense. Is it like getting warmer and warmer? Okay. I don't know what it does, but it's scary to let an infinite loop run on this. So I'm gonna put back the old code on it. And so name panic examples panic.rs. Oh, okay. But why do they have like another main then? That's a bit strange, but okay. I can do a panic. Let's do a panic. Nope. Just like so. What does it do when it panics? Out of curiosity. A panic occurred, yup, and then you have the backtrace thanks to discrete, I'm guessing. Okay. Yeah, that's something, I guess. Oh, and there is a little button to reset it. Can I? Is this one? Ooh, okay, that's nice. Alright. And so that doesn't do much, it just says yup. But so if we go into cargo.toml and we go profile release and debug. So now it's 2, I don't know what 2 is. Can we do this instead? And will it be more verbose or no, it's the same thing? Okay, so I already had what they wanted. Let's just put that back, remove the panic. Okay. We see, we still see a panic occur, but the backtrace is less helpful now. That is because the compiler omitted debug information and optimized the code. Okay, okay, so if I don't have debug information, it just prints question marks, but if I do, it kind of says like where, I guess. Oh, yeah, not sure. It's a bit more precise, I guess. That's because the compiler omitted. Yes, this will include debug information. Okay. Blinky. The iconic Blinky. Which I think I already did, but okay. Initiate the IO peripheral and create a LED variable from GPIO connected to the LED. Ah, okay, so it's not the LED built into the board, it's like an external LED. Alright, well, I have that. Here we can see that we can drive the pin high, low, or toggle it. Okay, that makes sense. And so there is plenty of, I don't know if I should show this. Yeah, of course, if I'm looking at it, I cannot really show it to the camera. So there is plenty of GPIO stuff. Is there? There's a ground there. There is 2 grounds. Oh, I see the UART stuff as well. There's a clock thing. Just curious. There is a 5 volt. There is a 3.3 volt. A bunch of grounds again. Then there is SMSPN, which I don't know what those are. Alright. Initialized a delay instance using toggle and delay MS method to make the LED blink every 500 milliseconds. Simulation. This project is available for simulation through 2 methods. There is a regular LED connected to GPIO 7. If you use okay, they want me to use their like dev kit, whatever. But I guess I don't really need it. Okay, I'm guessing that's something like an extra big board. Can't I just do Blinky myself? Just connecting to an LED to a GPIO pin. Shouldn't be that bad. Where is the example for this? This? So intro, where's Blinky? Blinky is there. And so I'm confused now if it's an example or in. Okay, so you're supposed to like implement it in the main, and in the example is the answer. Okay. So let's not cheat. Set GPIO as an output and set its high state initially. Okay, clock control. Maybe I should change that to boots defaults like they do. Oh, I have auto completion as well. That's nice. And so do they say like using the that's something that doesn't exist. GPIO ESP hole. What was the thing? Is there like a maybe like GPIO? Is there an example by any chance? So IO new peripherals GPIO, peripherals IO mux, IO pins GPIO 5 into push. Okay. I think that's what I want. The GPIO peripheral provides access to general purpose input-output pins on the SPI chip. This driver supports various operations on GPIO pins, including setting the pin mode, direction, and so on. Okay, maybe let's try to put this thing on the breadboard. But that's scary because I feel like I'm gonna break every single. Come on, buddy, I believe in you. Snap in. Snap in? No? Oh, I don't like doing this. Well, good thing I ordered 3 of them, because I'm gonna break the shit out of this, but... Okay, no, if I push too much, I'm gonna snap it in half. Well, it's half the way in. Oh, okay, never mind. Is it just because I have a shitty breadboard and I have another one that is a slightly better quality breadboard? Is this better? Oh yeah, it's much better. Okay, I'm just gonna take the higher quality breadboard. Oops, be right back. Alright, so I got the non-shitty breadboard, and so what do I want a ground and a GPIO. I'm way too close to the mic when I do this. So here's ground, here is a, I don't know, they want GPIO 7, but does it really matter? Funny, huh? I don't see like GPIO 1 or something. There you go, GPIO 4 is there. Okay. Okay, so we have the thing on the breadboard. Let's see how we do. Yeah, I don't remember what kind of resistance is needed for this thing. And I also forgot which one. Fuck. LED, cathode, anode. Can't believe I forgot this. This is. So this is a positive. So positive. Let's just do something like positive this way. I forgot to get some jumper cables. There we go, little jumpers. So let's put it there. And let's use a GPIO, what, 4? There you go, 5 is there. And so you go there. So that's, and then negative. Or cathode goes to ground, which is the last one. Oh, it already blinks. Well, there you go. I have a manual blinky. Cannot really see shit. I guess the pins are high by default. But this LED is either the LED is garbage or because it doesn't look good. Come on, do you have a bit of a more powerful LED by any chance? One that we can see on stream. Yes, that's better. Am I killing them? I don't know if you can see shit. Okay, well, it's on. And yes, I'm an electronics guy, am I right? Well, okay. I'm just gonna work with that, who cares? So, go there. Then we just need this. Don't think I need the hello world anymore. I mean, might always be nice to know that it's alive. Where does IO come from? So IO comes from GPIO IO. Okay. Can I do GPIO IO? Does that work? And so we can build this. Yes, works. Next, I have what is it called? Into pull push output, push pull output. And okay, it says GPIO 5, but I use, which one did I use? Oh, I used 5 as well. I used 5 as well, so into pull push, into push pull. push into push pull output, which returns GPIO pin, which we can do wait for high, wait for things, is high, is low. Can I set high, set low? Ah, that's what we want. So can't we just do ah, there is a toggle as well. Okay, so I just do LED. So toggle. Let's see. Yes, I have a blinking light. How awesome is that? So right, blinky is done. And yeah, controlling GPIO is very easy, as expected. But what can you do otherwise? You can set low, set high, set state. Then you have stuff to check if it's set high or set low. Then Steam, create a ping out of thin air. Into inverted pull up input. Into floating input. Configure the pin to operate on a floating input pin. Configure the pin to operate as a pulled up input pin. Set low, set high, set state. Into open drain output. Okay, basically there is a shit ton of stuff. But wait for high. Wait until the pin is high. If it is already high, return immediately. Ah. Wait for rising edge. Oh, okay, I see. Okay, so well, I have Blinky. Let's see. Where are the examples again? Okay, so that's the training. And so how do they do it? They just do this, and then they set high, and they toggle it. It's true that maybe I should... Well, it doesn't matter if... Like it's... Yeah, sure. Maybe it's a good practice to do LED set high, to know that it is always set high to start. And yeah, okay. Boom, 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 boom. Okay, that's it. Blinky is done. Next is detect a button press. We're now going to make the LED lit, licht. Doesn't sound like English. Only when we press a button, we will create a project that reads the state of a button GPIO and reacts to its state. Go to intro button. Yes. We do have buttons, I think. Huh? Yeah. So the only thing I need is... Oh, yeah, we do have buttons, right? Okay. And so what we want is to just maybe disconnect this because it's annoying to look at a blinking LED. I mean, I could just short it when I mean, short the connection when from the LED to the board whenever it's blinked, but that wouldn't be very embedded development like. Exercise. Most of the dev boards have a button. In our case, we'll use one of the labeled boot on GPIO 9. Initialize the IO peripherals and create variable for the LED and button. The LED can be created into... Yeah, that's what we did before. As well, the button can be obtained using input pull up output function. Ah, okay, so that's on their dev boards thingy, where they have a button connected to a GPIO connected already to it. But I think it's the same thing if I do the button myself, where I just have the button connected to, well, I guess the 3 volt. What is into pull up input? Push pull output. So configures the pin to operate in a push pull output pin. Ah, yeah, right. You can have output and input pin, and so I'm guessing this is gonna be input pin. The pull up I don't quite get. Where's the into inverted pull up as a pulled up input pin? Configure the pin to operate as a pulled down input pin. I don't really get the difference between up and down in this case, but I'm gonna assume that it's rather intuitive, as in if the stuff it receives is high, it's gonna be like set to high, and that's it. Maybe it has to do with like timings and stuff like this. Where's my stuff? Okay, so I want a button somewhere else, and I should have brought more jumper cables. There's more jumpers. So let's put the button somewhere like here. Maybe here. And we connect one of its end to. It's annoying because the board only allows me to access half of the pins because the breadboard is too small. Okay, it may look like retarded when I look at it, but we don't see that I'm looking at it. Yeah, there is no 5 volts on this, or like there is no power on this side, so I guess I'm gonna have to switch sides, which is fine. Huh? Let's just remove the stuff. Let's pull it up. Oh, if I can pull it up. Yes, I can. Let's just switch sides. If I can switch sides. Yes, okay. So, is there a ground somewhere here? Where's ground? Ground is there. Okay, so that's ground. And we are just gonna connect this to the end of the LED. Then we have whatever, I'm gonna use some other GPIO pin, let's say 13, whatever, to lit up the LED. Okay, so let's just make sure that still works. So now it's GPIO 13. Let's see. Okay, still works. That's good. That's good. Then we're just gonna have two other cables that are kind of fucked. Oh well. Let's see. I try to have another camera to show what I'm doing with my hands, but I mean, to be honest, it's not really interesting. I'm just connecting stuff to buttons and LEDs. So 3.3 volt is here. Let's just connect it to just one end of the of the button, and then let's just pick some random GPIO, which will be, sure, 25. Up. And so we need to do, this will be button, and GPIO 25, I said, and this is into pull up input, I think. And I think what we need, let's set it to low first. We don't need a delay anymore, so I'm guessing we can just omit that and not do that. And we can do if button is high, we toggle the LED. Ah yes, it doesn't. Into pull up. Yeah, I haven't checked what into pull up returns. Into pull up input. It returns the same thing actually, so we can do is high or is low. Yeah. Alright, so let's see if this works. Let's see. Yeah, stuff is. It absolutely does not work. Let's add a little delay so that I don't have 300 prints, and let's do print ln just boom, button is high, like so, is high. I mean, of course, it's gonna be false, but I still want to check. Oh, what was it before? How did they do the hello world thing? Oh, they just do log info. Okay, sure. Log info. Does that work? Seems to work. Boom, 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 boom. And so it's high. Oh, okay, so it's flashing the LED. Okay. So it's flashing the LED, but too fast. I'm guessing, because it's always high, and so... oh, I'm retarded as well. The LED isn't. Okay. So right now it's always high, and when I press it, it doesn't put it too low. So let's read maybe. That's always a good thing to do. Have a button on GPIO 9, sure. Initiate the IO peripherals and create a variable for the LED and button. The LED can be created into push-pull output function as before, while the button can be obtained using into pull-up input function. And I did plug it into GPIO 25. Hey, what's an ESP32? ESP32 is this chip. It's a microcontroller. Hello, finite impulse. And right now I'm just doing the kind of small exercise to understand how it works. And I'm programming it in Rust because I'm a cool kid. A cool kid that cannot lit an LED with a button, but a cool kid still. Similarly to turning a GPIO input in an output, we can turn it into an input. Then we can get the current state of the input pin, which is high, and similar functions. Why not C? Because I saw you could do it in Rust, and I was like, that seems fun. I didn't know you could do embedded systems with Rust. And yeah, since you can, I'm just gonna use Rust. I would like at some point to experiment with embedded system in C. Maybe by buying some more slightly more obscure or older embedded system where you have no choice but to use C. But yeah, I was curious. Actually, you can program microcontrollers with a shit ton of programming language nowadays. There is even MicroPython I saw, where which is used for the Raspberry Pi Pico or other stuff. So yeah. Similarly to turning in GPIO, then we can get the current state of the input pin with is high and similar functions. We can get the state with is high. Okay, yeah, that makes sense. In the LED loop, add some logic so that if the button is not pressed, the LED is lit. If the button is pressed, the LED is off. Okay. Maybe the GPIO only respond when it's 5 volt. Right now I have it on the 3.3 volt. Let's see if 5 volts makes a difference. So I think there is there is 2 pins that provide 3.3 and 5 volt power, and that's basically it. Let's see. It's true. No, it's always true. It is always true. And see, if I do button set, I guess there is no set low. Yeah, there is no set low. That makes sense since it's an input GPIO. Button is high, is low, degrade. Yeah, I don't think it's a software thing. I think I just didn't plug it in correctly. Yeah. And just to make sure I'm not insane, so is low is always false, right? Okay. Oh yeah, it's not is high, but even if I press it, it's always false. I mean, the fact that it's an input makes me think that I need to provide power to it, but maybe it's the opposite, where it needs to be connected to ground, and yeah, that doesn't make sense. That does not make sense. Yeah, I'm not sure. Let's see how they did it. Examples. So intro button examples. So they have the button, they have the thing, and if button is high, set high. If the button is low, okay. So that's exactly what I did. As an output and set its state high initially. I did pull up input, right? Yes. How does Python work on embedded system though? It's an interpret language, right? I don't know. It's called MicroPython, so I guess it's a subset of Python, and they managed to compile it. Like, it's not surprising that they could compile a smaller subset of Python. MicroPython is a lean and efficient implementation of the Python 3 programming language that includes a small subset of the Python standard library and is optimized to run on microcontrollers and in constrained environments. Yeah, I'm not sure. MicroPython is a full Python compiler. So yeah, it compiles Python. And runtime that runs on the bare metal. Alright, yeah, that makes more sense. Huh? How the hell do I fix my thing? Maybe the button is just kind of fucked. Is there like a button state? Get? No? Degrade into an slim mode, trying to... Okay, let's just check, because maybe I just didn't plug in the button low enough in the board. No, it's not the case. And this is GPIO 25, yeah. Also, I'm like... Interesting, yeah. I also saw you could run Lua on microcontrollers. Not sure how, but yeah. Maybe let's do this. Maybe I should just press the button longer since I have a delay. Like what if I... Okay, so now it's like always pressed. Doesn't work. Let me try another button. Oh, this one is kind of crooked. And I'm not crazy, right? The buttons work. I know those ones are different. Well, let me just pick one that I know works. Maybe so that I can eliminate the fact that it might be the button. Yep. Is there like... No. Right, let's see. And so 5 volts. No, doesn't change anything. Does not change anything. So yeah, I don't think it's a button. Let me just put that back. Oop. Should really get maybe find a way to put a camera on top as well, so that people can see. I mean, to be honest, it's just an LED and a button and a microcontroller. So strange. Yeah, maybe, sure. I haven't tried to put it to ground instead of putting it into like on one of the power pin. Boom, 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 boom. Let's see. Let's see. Oh, okay, finally. Okay, so the way it works is like okay, I had to plug it into ground. I'm retarded. Alright. Let's just so let's just make it so that this needs to be into ground. What was the problem? I was so the board has like a 5 volt power and a 3 volt power, and I was trying to like attach. So the button, the way a button works is it cuts the current, or it like opens it opens a path between the two wires you plug it in when you press it. And I was plugging it in, like I was plugging one end of the button into the GPIO and the other end into the power. And I was like, when I press the button, it's gonna allow the power to go through the GPIO. But apparently that's not how it works. It's like the GPIO provide the power, and if it sees that it gets grounded, it is set to low. So yeah, just something I had to know, I guess. I think when I did that on a Raspberry Pi in the olden times, it was the other way around, but maybe my memory is just fuzzy as well. So this guy needs to go there as well. Yeah, pretty stupid problem, but I'm a bit rusty. So this guy goes there, and let's see. Does this still work? Yeah. Yes. Okay. So what we want to do is if is low, we do set low. Ah non, parce que is low is no, is low is what I want. So set low and else we set the LED to high. Let's have no delay, no print, and yeah, let's see how it goes. Okay, it's flashing it. So now the LED is on, and when I press it, it goes out. When I unpress it, and yeah, so that works. Life is great. Okay. I hope I'm not burning up the LED though. But yeah, I'm happy as a clown. As a clam, they say. Don't know why they say this. But anyway, I have a blinking light. Let's go. Soon into space. Boom, 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 boom. Alright, let's just go through the next example, I guess. And maybe disable the light. Yep. Detect the button press. Okay, that's done. Detect the button press with interrupt. Okay. From what I remember when I try, I mean, not try, but I wrote a very small kernel. If I remember, interrupts are like when there is some set the IO pin as a pull up, so it is always pulled to 5 volts through the internal 10K resistor. The button it connects the ground to the IO pin to be read as 0. Ah, so that's what pulled up means. So if I set it to pull down, does it mean that it will be the opposite, where I need to provide it power for it to... Well, I'm curious now. Let's pull down. Sure, let's keep this for like so. And so I would need this time to, instead of this being there, can I use power? And I use at 5 volts, so I think so, but I'm not sure if the microcontroller has a pull down resistor. Well, it does say into pull down, so, well, fuck it, let's just try it. Huh? So I've connected it to 5 volt instead of... No, it doesn't work. It doesn't work, but okay. Oh, did I crash my whole computer? Never mind, I just was pressing the wrong key. Alright. Oh wait, I'm retarded, fuck. I forgot to plug in the LED because it's annoying me when it blinks. Alright, okay, never mind. It does work. So it is what it means, like the pull up and pull down. So pull up means that it's expecting the other end to be ground, to be high, and pull down means that it expects the other hand to be power for it to be high. I think that makes sense. It's like pull up. Yeah, okay, in my head it kind of makes sense. Alright, so okay, that's nice. That is nice. I mean, I got tricked by the book because they said I had to use the pull up. Anyhow, detect a button press with interrupt. Now, instead of polling the button pin, we use interrupts. Interrupts offer a mechanism by which the processor handles asynchronous events and fatal errors. Okay, so it's just the button is gonna trigger something, and interrupt is basically a jump that is provoked by some kind of I/O thing, I think. Exercise. Inspecting the code, the first thing we notice is the static button. We need it since the interrupt handler. We have to clear the pending interrupt on the button. Wait, let me just get the code under my eyes so it is clearer. I'm making a MS Paint clone just so that I can call it BS Paint. Pretty good reason to, yeah, just you don't need a lot of good reasons to just make stuff. BS Paint, pretty good. What about button interrupt? And so SRC, and there is some hints there. So indeed, they have a static button, which is, oh no, that's not gonna be fun. Mutex ref cell. God damn, I've seen those before. They're not fucking mutex ref cell. Option GPIO 9 input pull up. Okay. It's an optional GPIO. And so LED button. And so there is a handler. Critical section with CS. Print out GPIO interrupt button. Yeah, that's some like ref cell stuff. Unwrap. Clear interrupt. Okay, so that's like the return, and that's in between here we can put whatever code we want. So I'm guessing LED up in this case, and is a CS like a context, or is a CS something else? Borrow ref mute. Anyway, let's just read a bit. Inspecting the code, the first thing we notice is the static button. We need it since the interrupt handler. We have to clear the pending interrupt on the button, and we somehow need to pass the button from the main to the interrupt handler. We somehow need to pass the button from the main to the interrupt handler. Okay. Yeah, so it has to be like a global variable, because it's gonna be shared between the main and the handler. Maybe. Since an interrupt handler can have arguments, we need a static to get the button into the interrupt handler. Since the interrupt can't have arguments. Ah, okay, I see. We need the mutex to make access to the button safe. Please note that this is not the mutex you might know from libstd. This is a mutex from critical section, and that's why we need to add it as a dependency. And so critical section is like cross-platform critical section. Alright, so it's like a more embedded system version of mutexes, and like how to make struct or like object safe across different parts of the execution. I don't know how to explain this. We need to set the interrupt handler for the GPIO interrupts. We need to set the interrupt handler for the... Okay. Okay, so I'm guessing in the... somewhere here there is a... Oops, I destroyed your ears maybe. Interrupt... No? Set to input, enable input. Connect input to peripheral. Is there an interrupt thing? There is. I cannot write interrupt apparently. Okay, so maybe there was an interrupt here. Interrupt with... Okay, there is interrupt with 2R. Is interrupt set? Clear interrupt. How do I set interrupt? Check if listening for interrupts is enabled for this pin. So I need to listen with option. Set configure an alternate function. Sleep mode. Set state, set high, set state, set low. And so interrupt, clear interrupt. Listen for interrupts. Okay. And so event, rising edge, falling edge, okay. How do I assign a handler for to this though? Okay. Set interrupt handler for the GPIO interrupts. Let's add a critical section using the with method and enable an interrupt for falling edges. Okay, let's just copy part of what they have written. So I do handler, fn handler, so pretty, need to use critical section. Don't have this. Don't have critical sections. I'm guessing I need to cargo add a critical section. Okay, so this exists critical section with CS, which I don't know what that means. Oh, CS probably means just critical section, probably just a context thingy. Okay. Static handler is never used, sure. Print ln GPIO interrupt. Do I have println? No, I don't have println. Sure, let's just do use ESP println. So, okay. Then we need to clear the interrupt. And first, we need a global static variable button, which is a mutex to a ref cell, to an option, to a GPIO, in my case 25, which is input, pull up, fuck's sake. And then it's a lot of write, so it's like input, GPIO, option, ref, cell, mutex. Don't we love to program in Rust? And it is equal to mutex, new, ref, cell, new, and I guess none, like so. Okay, I'm one too many. Okay. Just wondering, as you're about to detect falling edges from 1 to 0, should you change the wiring back to button ground and use the pull up? Then the signal would go 1 0 as you press the button. Yeah. I mean, I'm just using the example. I guess I could also just do pull down here, which would be the same, I assume, which would work in my case. But sure, yeah, you are right. Let's put it back to pull up. And this should be the same, although I'm missing some imports. So from GPIO, I can import all of those. GPIO 25, IO, I'm guessing input as well, and pull up. Then I need to include mutex, which is from is mutex. Rust syntax makes my head spin. Yeah, I mean, this is okay. Like, most of it is okay. This thing where there is a mutex ref cell is always a nightmare. But oh well. Oh well. I could do like type GPIO 25. I don't know. I could call it like button GPIO and do like this. And so 1, 2, 3. And make a type alias. That would maybe work. Let's see. Can't I do this? Expected one of the... Trying to make it slightly clearer. If you use pull down, I think you'll detect when the button is released. Maybe try it out when you get this one working. Yep, we'll definitely try it out. Wait, it's only 2? Yeah, it's only 2, okay. And here there is the option one, there is the ref cell one, and there is the mutex one. Okay. Finally, and so use core cell, ref cell as well. Okay. Is never used. What the fuck are you talking about? It's used just below. Okay, I mean, he's not happy that I did type alias, but I think I understand it a bit better that way. So at least it compiles now. Here I have to clear the interrupt. How do they clear the interrupt? They do button and all the mutex ref cell garbage. So they do button. No, borrow ref mute, and then as mutable, then unwrap, and then clear interrupt. Okay. Oh, and here we need this apparently. Borrow data and call. This is equivalent to self borrow, CS, borrow, mute. Alright. Okay. So wait, you're right. Let me put it back to ground before I forget actually. Alright, back into ground. Then I need to set the interrupt. I need to say this function is the interrupt handler. We need to set an interrupt handler. We need to set an interrupt handler for the GPIO interrupts. Let's add a critical section using with method to enable an interrupt for falling edges. Critical section with CS, button listen, event falling edge. In this line, we move our button into the static button for the interrupt handler to get hold of it. The code running inside the critical section with closure runs within a critical section. CS is a token that you can use to prove that to some API. The interrupt handler is defined via the handler macro. Here, the name of the function must match the interrupt. So there is this thing that needs to go somewhere. So the LED stuff is still the same. The button will be different. I don't know, let's do that maybe. So button, oh wait, no, button is still that way? Ah, okay, so that's where we set the button. Okay. I get it. So we still have to get the button. Then event. What is events? I'm guessing it's part of GPIO as well. Event. Cannot borrow button as mutable. Now can you? Yes, you can. Can I build it? Yes, I can. So falling edge would be from high to low. And that's what I have right now, okay. So button listen, falling edge. Button replace this. And now I need to link this handler with the button. So the button is listening when there will be a press. So there is a listen with options, sleep mode, number, alternate function. Configure an alternate function. Doesn't sound like an interrupt. Is interrupt set? Check if the interrupt status bit for being set. Clear interrupt. Listen for interrupts. Okay, but how do I know? Like, how do I connect them? How do I connect them? Clone unchecked. Connect peripheral to output, internal output. Is low, is high, disconnect, connect, enable, set to low, set to high from. Check if listening for interrupts is enabled for this bin. They say anything else in the book. Let's add a critical section using with method to enable an interrupt for falling edges. And I understand that we enable it. How do I link it? In this line, we move our button into the static button that I understood as well with the replace thingy here. For the interrupt handler to get hold of it. Okay, the code running inside the name of the function must match the interrupt. The interrupt handler is defined via the handler macro. Here, the name of the function must match the interrupt. The name of the function must match the interrupt? Yeah, I'm really confused. I'm just gonna look at the... Yeah, there is nothing else for me to... What is the example? How do you connect the stuff? I'm so confused. How does he know that the handler is the handler for this one? because that's what I have. Okay. Sure, let's LED online 29 of their example. Oh, I'm blind. Oh, I'm blind. Okay, that's nice. Yeah, true. I could have just looked in the freaking doc, like interrupt, and then looked for handler here. Yeah, I got a bit lazy, I guess. Set interrupt handler. Okay, yep. Yep, that makes more sense. That makes more sense of the document before. Yeah. Yeah, I don't know. I got lazy set interrupt handler to when I just first handler. Yes. And so now I don't understand. Like when I'm gonna press the button, it's gonna go to this section of the code. And when this function returns, it's gonna jump back where we are. But in their example, they do like a toggle constantly. So iOS mutable. Okay, let's just make it mutable. So what I would guess that does is that just pauses the blinking because it's gonna blink. Let's see. Can I hold it here? So yeah, the LED is blinking, and when I press the button, oh okay, okay, it just keeps blinking. But if I press it fast enough, does it like? No, okay, retarded. Yeah, I guess since it takes like 0 time to toggle it, we won't see a difference. But it's weird. I thought we were supposed to detect a button. Oh, it's just detecting a button press. It's not like changing the LED with the button press. Okay. So the LED just blinks. And we make sure that... Okay, so the goal of this is kind of like async programming, I guess. If you put a delay where... Ah, yeah, true. Let's see. Oh, am I supposed to recreate a delay here? So let's delay and create a delay of, let's make it 2 seconds. That's a good suggestions. Otherwise, but does it work? Because can I just? I don't want to freeze it because freeze it like changes the clock rate. Can I have this into? Okay, I don't know. That doesn't look right, but I'm gonna try it. How can I? How could I share this kind of stuff with the? Fingers crossed. Yeah. I mean, there is no risk I'm gonna break it with that kind of shit. I mean, it does stuff, it still blinks. Okay. So it's blinking. Let's press the button. Ah. Well. Oh well. Yeah. But yeah, I get your point. Like, if there would be a big delay or a big computation here, it would stop the main program and it would stop the main program and at least it paused. Yeah, true. Actually, it worked. So good suggestions. Mon dieu. Alright, but yeah, I get the point. It's like kind of asynchronous programming where you can jump to a part of jump to some instructions, finish them, and go back where you were, and then keep executing. And like you don't have to constantly like there is some like hardware stuff listening for you, well, you don't have to like explicitly have a loop that checks if an event is high or not. I guess that's what it's doing under the hood, maybe. Maybe not actually. Oh well, doesn't matter. So yeah, that's pretty cool. What is the next one? DMA. The DMA peripheral is used to perform memory transfers in parallel to the work of the processor, the execution of the main program. In this chapter, you will learn how to use DMA with ESP Hall. For the example, we are going to use the SPI peripheral. Used to perform memory transfer in parallel. In this chapter, you will learn how to use the DMA. With, for example, we are going to use the SPI peripheral. What is serial peripheral interface? Is this just for like a serial port? Or is it just like a standard and I don't know. I've heard this before though. Okay. Poum. DMA. Cerci. Main. Okay, so let me remove the handler thing. Maybe I should quickly commit my stuff now that I think about it. Initial commit, just to make sure I still have the interrupt example somewhere. Interrupt with a button. No GPG sign, like this. Alright, let's see. So they import some SPI stuff and some DMA stuff. SPI, new peripherals. This, is there like a... Let me disable the LED. Is there like a, I see SD2. There's SP. SD1. Yeah. SPI. New peripheral SPI2. 100 kHz. SPI mode. Clocks with pins. Ah, okay. I think I kinda get it. Where you put, okay. Yeah, it's called general purpose input output. So what you do is just get some GPIO pins and then create some kind of, I don't know, SPI port with those pins. But those pins are like the GPIO pins. Okay. That makes sense. And let me delay. Encore, transfer. To transfer a much larger amount of data, we can use DMA. The CPU can ever do other things while the transfer is in progress. Oh, that's cool. Okay, that's nice. So I guess there is maybe some kind of chip that handles like DMA or SPI stuff. I'm guessing more DMA, where it can like transfer data while the CPU is doing something else. And so it just transfers data and so on and so on. Okay. That's good. Okay. Exercise. The project skeleton contains code to transfer a small amount of data via SPI. To make it easy to explore the example, you can connect GPIO 4 and GPIO 2. This way, the data we sent is also the data we receive. Oh, okay. Ah, it's like for input and output. Okay, okay. Where is the thing? So yeah, they have like very obscure names. uh, how do we? And so the goal is to write it, but also read it, I guess. And okay, so like GPIO2 would be read and GPIO2 would be write. And so if we connect the two, we... Okay. Okay. The blocking SPI transfer looks like this. Okay, so that's... Oh, okay, that's blocking. The data array SCLK clock signal, okay. I'm guessing the other two are read and write, like where the data is actually put. Master in, so yeah, and the other is master out, slave in. And the last one is CS. Yeah, okay. I'm just gonna write the full name in my code because there is no way I'm gonna remember that otherwise. Oops, slave in on the last one. Yeah, but yeah, I get it. I get it. So no more LEDs, no more buttons, no more this. Actually, I can just remove this since I committed. Still need the IO. Sure. This is all still the same. This all still the same. The handler we can remove. This we can remove. LED, there is no more LED. So let's do clock signal is equal to IO pins GPIO. I don't know, let's just do like mock stuff, and so there is master in slave out and master out slave in. Then there is a and the CS I don't know, so I'm just going to call it CS. But thank you for the rest. And so this is SC, okay. So S for signal and clock for clock, that makes sense. This is just MESO. Yeah, this is the other way around, MOSE. Maybe it help you follow the tutorial later if you use the generally used names, those names, chip select, okay. Chip select this, and comment the meaning to the code. Yeah, I think though. Okay, so I think like 3 out of 4 I understand. Like the chip select, not sure. But this is basically master in would be read, master out would be write, I think. I think this is read, this is write. And clock is the clock, chip select, I'm not sure. Man, what's up? Long time no see. Yep, I've taken a bit of a break. But now doing some embedded development in Rust. And so let me pick some. So yeah, this is what I'm doing basically. There's a microcontroller and doing some stuff on it. Currently trying to transfer data in and out. Oh, my stuff is kind of funky. Oh well. Let's remove this. Whatever. Who cares about the button and the LED? And so I need Can I just put the clock signal and the chip select to the void? Because there is, like I'm writing to myself. So can I just put, I don't know, let's pick, there's 4. So 12 is gonna be the clock. Which I'm just gonna put to ground for now. Chip select is gonna be 14, which I'm just gonna put to ground. And then, yeah, but that's annoying because my breadboard, fuck. I have to, because there is, I mean, I don't know if you can see, but there is only one row of available, like, stuff to plug stuff in. Can I, I'm afraid I'm gonna break it every time I pull it out, but oh well. Which looks like what I'm doing. Can I put it to the side like so? Yes, so that now it's a bit to the side and I have more room to plug in stuff. So 12 and 14 are the, let's just do it now. So this is 12, this will be 14. And what are 2 other GPIO stuff? Ah, but I only need 1 wire. I'm retarded, okay. I didn't need to do that. So, yeah, 32 and 33 will be read and write. So yeah, I basically have like 2 wires that go to ground. Oh wait, that's not ground. 2 wires that go to ground. Where's ground? Ground is there. Boom, 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 boom. Yeah. Oop. What is the truly chaotic good way of wiring up the controller on the breadboard? Good. What a truly... yeah. You like that scuffed setup where it's on the side, you know? Like, I don't know. You call it chaotic, I call it creative, okay? Anyway, I just connected the read to the write, and so that's 33 and 32. 32, 33, like so. So, let me just copy what is in the example into, oops, import a bunch of SPI stuff. Boom, 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 boom. Like so. And also DMA stuff. And DMA buffers for some reason. Okay. Okay, those are all stuff that exists. That's nice. And so in their example, in the start of their example, they set up the SPI, shall I call it a port? I don't know. Let's mute SPI, like the SPI interface. The serial interface, I should call it, I think. SPI new peripherals SPI2. Then 100 U32 to K, what do they call it? Go away. Up. Kilohertz, which I'm guessing is the clock rate. Why are some of the numbers colored differently in the number line? Ah, yeah, that's just a plugin I use called Git Gutters, I think, which just shows, like, in green the stuff you've added since the last commit, red the stuff you deleted, and in blue the stuff you modified. Sorry if I blow out your eardrums. SPI mode is mode 0. Maybe I should learn a bit more about that. And I also have 2 clocks. Oh, by the way, Ansi, I'm gonna butcher your last name if I try to pronounce it, but your first name is like the ANSI standard in C, so that's quite nice. Do you know what chip select means? Is it like, I remember to play with some other chips where it was like if the chip is on or off, or like how to, like when it's oh, I'm guessing it's like to notify the other chip that we're sending data, like it's set to high or too low to indicate that data is about to be sent to like whatever other chip is listening. Yeah, I think it has something to do with the fact if you use multiple SPI device. Okay, never mind. I said garbage. And then with pins, boom, and this is some clock signal. Then you have like 4 more. Oops. Really? Oh. This is master in, slave out. This is master out, slave in. This is chip select. Peripherals. Like this? Yeah. Right, I gotta go. Yeah. See you. Multiply SPI device. Remove this mode. Yeah, it's not needed for now, but it will be needed later. And so, let's do what they do. Essentially, if you have two SPI devices, you set the target devices C has high to tell the target that data is going to be transferred. Okay. You mean two SPI devices coming through the chip, like going inside of the chip, because... Or is it like if you're transferring to two different chips, or like you have the possibility to transferring to two other targets, and like one is a chip select low and the other is chip select high, or something like that? Oh my bad, ESP32 and two other devices. Okay, yeah. Yeah, I think that makes sense in my head as well. Okay, but if I just put it to ground, yeah, should be fine. Or maybe I should connect the... No, never mind. Never mind. So mute data is just a slice of bytes. And I just do like U8, and then okay, they just do 1, 2, 3. 1, 2, 3, 4. Slice of an array of data. SPI transfer, which apparently doesn't work. Mutable data and wrap, like so. Can I build it? Can I go build? Yes, I can build it. That's something. So, okay, the data array in this case serves as the data to transmit as well as the buffer to receive data. Ah, okay, that makes sense. The first, I mean, that makes sense. That's a bit strange, but okay, whatever. As data array, first thing we need to use DMA is initializing the DMA peripheral driver and getting a channel. And so DMA is direct memory access. So SPI is a peripheral and DMA is what, the standard of, or is it like a... First thing we need to use DMA is initializing the DMA peripheral driver and getting a channel. We also need to create a buffer for data we want to send, as well as a separate buffer for data we will receive. And that is not in the example, right? Boom. No, it's not. Okay. Let's so let DMA is equal to DMA new peripherals DMA, let DMA channel is equal to DMA channel 0. Okay, sure. And apparently it doesn't exist. Unknown field. Let's fix that later. But then you get a transmitter and a receiver. Okay, let me just copy paste this. Which is a bit like message queues in the end. Okay. There are also descriptors needed. That is because internally the DMA peripheral uses a linked list for the transfer, and that is what the descriptors are needed for. For convenience, we use the DMA buffers macro to create the buffers and the descriptor. You could use cargo expand or cost analyzer to expand the macro. Comment to see what code the macro expands to. Oh, that's nice. Next, we need to configure the SPI peripheral driver to use DMA. Okay. Where's DMA? Okay. So I'm guessing DMA is like some kind of protocol slash implementation of that protocol. So we create it here, which I mean, there is still an error, but okay. So we can do, yeah, let's just put that on a new line. Yeah, never mind, maybe that's good like this, and then I do with DMA. DMA channel configure, and the ports, they have mute TX descriptors, they have mute RX descriptors, they have DMA priority, which is priority 0, and they have, yeah, closing the things. Yeah. Now we are ready to start DMA enabled SPI transfer. Now we think I should watch a video about what DMA is and SPI is. SPI I think I understand, but still. Now we are ready to... So let transfer is equal to SPI. I'm getting a bit confused, but also I have a compilation error here. So let's just search for that in the thing. DMA. So there is DMA. DMA driver provides an interface to efficiently transfer data between different memory regions within the ESP microcontroller without involving the CPU. Oh, without involving the CPU. That's cool. The direct memory access controller is a hardware block responsible for managing this data transfer. Oh, I see. That's really nice. So like the CPU can chill and someone else is taking care of the data transfer. The driver is organized into several components and traits, each responsible for handling specific functionalities of the DMA controller. Below is an overview of the main components and their functionalities. Yes, register access. And I do channel 0, but in my case it it doesn't work. It does not work. Channel. Let's see what new returns. So here is DMA. Here is DMA, and then there is a new. I'll return the DMA. Oh. And it doesn't say anything about SPI2 channels. Maybe it's just some old code, and now it's named SPI2 channel or something. Can I change the version by chance? Can I look at an other version of the documentation? Doesn't look like it. Let's try at random this one, because it mentions SPI. It does mention SPI, so channel 0 question mark. Okay, and then let transfer is equal to SPI DMA transfer. Now we need to pass the buffers to transmit and receive individually. Please note that these will now get a DMA transfer from calling transmit. What happens here is that the buffer and the SPI driver are moved into the transfer. We get this way the buffers and the driver are inaccessible during the transfer. Now we are free to let the CPU do other things while the SPI transfer is in progress. Okay, DMA transfer will move the driver and the buffers into the returned transfer. The drivers and the buffers. Okay. Okay, so let transfer is equal to DMA channel? No. SPI DMA transfer. Mute TX buffer mute RX buffer. Is that it? Yeah. And then run. But this, can I compile this? Oh yeah, I can. Okay. Yeah. Okay. Wait for the transfer to complete and get back the buffers and the driver instance. As mentioned before, the buffers and the driver are moved into the transfer. Transfer, wait, update. The buffer and the SPI are moved into the transfer. Okay, so we wait for it. Transfer, wait. Okay. We can wait on the transfer, it will block until the transfer is done, and we get our SPI driver and the buffers. While using DMA needs more effort than letting the CPU do all the work, it's not too complex once the general ID is understood. You might assume that it's always preferable to use DMA. That's not the case. Setting up DMA transfer consumes more CPU cycle than setting up a blocking transfer. Especially if the amount of data to transfer is small, this might hurt performance a lot. Also, if there is nothing to do for the CPU other than waiting for the transfer to finish, it's preferable to use a blocking transfer. Okay, so it's for like larger amount of data. or if we need to absolutely not block. However, if the amount of data transfer is bigger than the time needed to set up the transfer is negligible compared to the time the CPU could use to do useful things in parallel. Okay. And so can I just read the buffer? Like, what do I do then? Okay. How do I transfer the data? Yeah, I'm getting a bit confused. I'm gonna cheat because I'm hungry. So okay. So this is a blocking thing. Transfer much larger amount of data, we can use DMA and the CPU can do another thing while transfer is in progress. So let's suppose that I don't care about DMA for now, and let's just do a blocking write and read. So I don't care about this, I don't care about this, and the thing we need is int ln, like so, and it prints it this way, data. Ah, okay, it wasn't, transfer wasn't defined because I had this, okay. Run. Let's see. Ah, okay. So every 2.5 seconds, it will write data and also read the same data, and the CPU takes care of it. Okay, that makes sense. And now let's use DMA. I mean, we can, but I need to retrieve the data some other way. And also create this, create this thing. So yeah, I'm not printing anything, so we won't know what the fuck it's doing. So yeah, nothing happened. And sure, let's maybe, how do you call it? Channel. So I use this one. So I have configure async. Is there anything like read writes? Buffer. DMA. How do I read the buffer? Or what is the buffer? Peripheral DMA. DMA buffers. Yes. Are bytes passing only parameter. Oh, can I? Ah, okay, so you declare the number of bytes that are here. Can I just print it? Rx buffer. Oh, can I build it and run it? Okay, I get it. And so, well, first I would like a buffer that is smaller, so 10 elements. And can I do like, so it's mutable, so can I do for I in 0, 10. We do transmission buffer I is equal to I. Expected you do type A. So that doesn't work. Found use size. Ah, yes. As you wait. Yes. Can I do this? All right. Okay, and it's okay. Yeah, that's really cool. And so, but and here the only difference is that during the transfer, the CPU can chill and do whatever the fuck he wants, and the data reading and writing is taken care of by another chip. Okay, that makes sense. I'm gonna go eat and maybe come back this afternoon for to continue on this, or maybe not. And yeah, see you for another stream, or see you for a nice day. Thank you, Ansi, for like the tips. That was really nice, like explaining basic concepts to the noob that I am. And yeah, see you later. See you later.